Bismillahirrahmanirrahim. Assalamu-Alaikum warahmatullahi wabarakatuh. Dear students, me, Professor Muhammad Asif Qureshi, working as Assistant Professor of Chemistry at Government Boys Degree College, Islamabad, Hyderabad, once again in front of you with a new and fresh lecture. And that lecture is in continuation of my previous lecture which I delivered a few days back. The chapter was chapter number 3, Atomic Structure. That was part 1 of this lecture, and today I am with you with the another part 2 of the same topic, electronic configuration. I have written the definition of the term electronic configuration again for you people so that you can recall your memories. The electronic configuration is the process of distribution of electrons among various subshells of an atom, and the rules of electronic configuration are about 3 or 4, out of which the first rule, first principle, we already discussed in our previous lecture. That was Aufbau principle, which was given by Pauli. Now, today, the new topic with which I am going to start my today's lecture is Hund's rule of maximum multiplicity. As the name indicates, that the rule was given by the scientist Hund. The statement of the rule says electrons are distributed among the orbitals of an atom in such a way that the maximum number of unpaired electrons have the same direction of spin. Dear students, this statement of the rule says that when you are going to fill up the electrons in various orbitals of an atom, you have to fill up the electrons singly first, having same direction of spin. When all the vacant orbitals become filled with one electron each, showing same direction of spin, then the pairing of electrons will take place in the opposite direction of spin in all the orbitals. So this is the simple statement of Hund's rule of maximum multiplicity. My dear students, on the basis of Hund's rule, if we try to write the electronic configuration of few elements in the periodic table, for example, if I talk about carbon, whose atomic number is 6, you remember that on the basis of Aufbau principle, the configuration of carbon 6 can be written like this. But if I make the configuration of carbon on the basis of Hund's rule now, first of all, I have written all the orbitals available in the carbon atom. Now, the first electron to be added in all the available orbitals will have the same spin, which will be clockwise spin. Now the pairing of electron takes place, showing that the first orbit K is completed here, 1s2, and the second orbit L has 4 unpaired electrons, one in the 2s orbital, other is in the 2px orbital, then third one is in the 2py orbital, and fourth one is 2pz orbital. And this is the configuration according to Hund's rule. Similarly, when we talk about the configuration of nitrogen, atomic number 7, on the basis of Aufbau principle, the configuration of nitrogen is written in this way. But when we use Hund's rule, electron to be added will have same spin, parallel spin, that is clockwise spin. The second electron added will have the opposite spin, paired spin, that is anti-clockwise. So this shows the K shell complete. While in the L shell, the configuration of nitrogen is taken 2s2 and 2p3, having one electron each in the 2px, 2py and 2pz orbitals. Similarly, when we talk about the configuration of oxygen on the basis of Aufbau principle, we write it as 1s2, 2s2, 2p4, showing that K shell is complete while L shall have 6 electrons. If I write the same configuration of oxygen on the basis of Hund's rule, I have to write all the available orbitals first. Now the first electron to be filled will have the clockwise spin. Now the pairing of electron takes place. This is the 1s2 showing the K shell is complete, 2s2, 2px2, 2py1, 2pz1. So these are the 6 electrons added in the L shell of oxygen atom. Second shell 2s2, 2px has 2 electrons, while 2py and 2pz has only 1 electron. So this is the way to write the configuration of any element based upon Hund's rule of maximum multiplicity, and it is the rule or principle which we use to calculate the valency of an element rather. So to calculate the valency of an element, we use the configuration based upon Hund's rule of maximum multiplicity. Now my dear students, I have to go through few concluding points of Hund's rule, which I'm going to write on the board for you, and then I am going to explain those concluding points of Hund's rule to you people. There are a few concluding points about the Hund's rule of maximum multiplicity, which are to be illustrated right now, and you have to understand, you have to go through these important points. The first point of Hund's rule says that maximum number of orbitals in a particular energy level. Energy level, my dear students, means shell, which are K, L, M, N, O, P, Q. So the maximum number of orbitals or sub-energy levels in a particular energy level is equal to the formula as shown by the formula n square. For example, if we are having K shell for which n equals to 1, so 1 whole square will give 1 sub-level, 1 orbital in the K shell. I must explain it as, if I take n1, then I am talking about the K shell. The formula n square shows that it is 1 square means 1, so there will be only 1 orbital, which is the s orbital present in the K shell. Likewise, if I talk about the second shell L, for which the value of n is taken 2, formula n square suggests that it is 2 square, means total number of orbitals present in the L shell will be 4. Similarly, when I talk about the third shell M, I take the value of N3 for M shell, putting the value 3 in the formula, there are 9 orbitals in the third shell M, and in the same way, if I am talking about the N shell, for which number of orbit is written as 4, formula n square suggests in all there must be 16 orbitals in the fourth shell N. So this is the first concluding point of Hund's rule, which says that the maximum number of orbitals in a particular energy level is equal to the formula, is shown by the formula n square. Second point says, in an orbital, when I say orbital, I am talking about s orbital, p orbital, d orbital, f orbital. So second point of Hund's rule says, an orbital cannot contain more than 2 electrons, and this was explained by Wolf and Pauli in his principle, which was known as Pauli's exclusion principle as well. An orbital can have maximum number of 2 electrons in it. Third point says, maximum number of electrons in a particular energy level. Energy levels of shells are specified by the symbol n. So the maximum number of electrons in a particular energy level, which is denoted by the symbol n, is shown by the formula 2n square. So putting the value of n in this formula, you can have the maximum number of electrons for k, l, m and n shells as 2 electrons in the k shell, 8 electrons in the l shell, 18 electrons in the m shell and 32 electrons in the m shell. If I give you some examples to explain this point further, if we take the value of n1, means we talk about k shell. The formula 2n square suggests maximum number of 2 electrons in k shell. Similarly, if n is taken 2, it indicates the second shell L. The formula 2n square suggests that there will be 8 electrons in the second shell, L shell. In the same way, if n is taken 3, the third shell which we talk about is M shell. Putting the value 3 in the formula, you will have 2 into 9 means 18 electrons in the M shell. Likewise, if we take N4, then the fourth shell is the N shell. Putting the value of N4 in the formula, we find the number of maximum electrons 32, which can be accommodated in the N shell. So this is the third concluding point of Hund's rule. The fourth point says the number of sub-levels, sub-energy levels, SPEF we are talking about, in an energy level is specified by n. Energy levels are specified by n. So the number of sub-levels in an energy level is equal to the value of n itself. What does it indicate, my dear students? If we take n1, means we talk about the first shell k. So the k shell itself has only one subshell, which is the S subshell. In the same way, if I am talking about the second shell, L shell, so the value of n is taken 2 here, it means that L shell has 2 subshells, which are S and P subshells. Similarly, if we talk about third shell, M shell, means 3 3 subshells will be there, which will be S, P and D subshells. In the same way, if we talk about the fourth shell for which n is taken 4, there will be 4 subshells S, P, D and F in the fourth energy level, fourth shell. Going through the fifth concluding point of Hund's rule, my dear students, this point says the number of orbitals in a sub-energy level. Sub-energy levels are SPDF and they are designated by the symbol L, which is the azimuthal quantum number. So the sub-energy levels specified by the symbol L. Number of orbitals they contain is shown by the formula 2L plus 1. For example, when I talk about S subshell, P subshell, D subshell and F subshell, the L values for these subshells are taken 0, 1, 2 and 3 respectively. Means if I talk about L0, means I am talking about S subshell. For L1 it is P subshell, for L2 it is D subshell and for L3 it is F subshell. So putting the values of L in the formula, we can calculate the number of orbitals. For example, if I take L0, means I am talking about S subshell. For S subshell, the formula says 2 into 0 plus 1. 2 into 0 makes 0, plus 1 means 1. So S subshell has only one orbital, and then one orbital is itself the S orbital rather. So S subshell has its own one S orbital only, it has no any orbital. When we talk about L1, it means we talk about the P subshell, putting the value 1 in the formula 2 into 1 plus 1, 2 1s are 2 plus 1, total number of orbitals in the P subshell are 3, and that those 3 P orbitals are the Px, Py and Pz orbitals. Likewise, if we take L2, means we talk about the third subshell, D subshell, putting the value 2 in the formula 2L plus 1, we get 2 to the 4 plus 1, 5 orbitals in the D subshell, and those 5 orbitals in the D subshell are dxy, dyz, dzx, dzx2, y2 and dz2. In the same way, if we take L3, for which the subshell comes out F subshell, the formula says 2 into 3, 6 plus 1, 7 orbitals in the F subshell. Now, so these are the number of orbitals calculated by the formula 2L plus 1 in any sub-energy level or subshell specified by the symbol L. Dear students, the sixth concluding point of Hund's rule says the maximum number of electrons in an energy sublevel. Energy sublevels are denoted by the symbol L. So the formula showing the maximum number of electrons in an energy sublevel is formula 2 into 2L plus 1. So we say for S, P, D and F subshells, the number of electrons will be 2 in the S subshell, 6 in the P subshell, 10 in the D subshell and 14 in the F subshell. I can give you some examples using the formula. If I take L0, means I talk about S subshell. Putting the value 0 in the formula, 2 into 0 plus 1, in S subshell, number of electrons present will be 2 only. Similarly, if I take L1, then I talk about P subshell, using the value of L1 in the formula, the maximum number of electrons in p subshell will be 6. In the same way, if L is taken 2, then the D subshell putting the value for D subshell 3 in the formula, we have the value of L is taken 2 for D subshell. So I take 2 here, it becomes 4 plus 1 now, and 4 1 plus becomes 5. So the number of electrons that can be accommodated in the D subshell is 10. In the same way, if I take the maximum value 3 of L, it means that I talk about the F subshell. The F subshell, putting the value 3 in the formula, maximum number of electrons that the F subshell can have is 14. And the last and the most important point of the Hund's rule says, to represent the number of electrons in any subshell of an atom, the notation used is NLX. Dear students, try to understand this notation. N is the number of shell, number of orbit, which is having the value 1, 2, 3, 4 and so on. L is the subshell like SPDF, and XC is the number of electrons present in the subshell. So N may be in this formula, in this notation, N may be 1, 2, 3, 4 and so on. L may be SPDF, while X may be 2, 6, 10 or 14 electrons. For example, if I write 1s2, 1 shows N, S shows L, and 2 shows the value of X here. So 1 is the shell, S is the subshell, 2 is the maximum number of electrons which can be accommodated in the S orbital of first shell.